If switch S1 and S2 are open, give the reading on V2. When that is the case, let's look at S1. There won't be any current flowing in this direction. And when S2 is open, there won't be any current flowing in that direction. Why do I say so? The only path is the voltmeter, and no current can flow through that voltmeter. What V2 will be reading is the EMF, which is 6 volts. With only S1 closed, the ammeter records a reading of 0.75 ampere. Explain the meaning of 0.75 ampere. So we know that the current is equal to the charge in coulombs divided by the time in seconds. So if the reading on the ammeter is 0.75 ampere, then this tells us that 0.75 coulombs passes a point in 1 second. Anyway, let's go to 8.3.1. With only S1 closed, calculate the external resistance of the circuit. So let's go ahead and close S1 and see what happens. If S1 is closed, then this 3 ohm resistor and the 1 ohm resistor are parallel with the resistor R. So we can say that the EMF is equal to I multiplied by R external plus the internal resistance. Do we have the EMF? Yes, we do. That is 6 volts. Do we have the current? It is said to be equal to 0.75 when S1 is closed. So we have 0.75 multiplied by R external plus the internal resistance. The internal resistance is said to be 0.4 ohms. So we have 0.4. What we need to do now is to divide both sides by 0.75. We will have 8 is equal to R external plus 0.4. It will be easy to see that R external is equal to 7.6 ohms, 8.3.1. What about 8.3.2? We're looking for the resistance of resistor R. Well, we just calculated R external. We know that R external is equal to RP plus RS, the resistance in parallel plus the resistance in series. So R external, that is 7.6. RP is what we're going to use to find the resistance of resistor R, plus RS, the resistor in series, that is 4 ohm. So if we rearrange this and make RP the circuit of the formula, we're going to get 7.6 minus 4. So RP is equal to 3.6 ohm. Now we can go ahead and find the resistance of resistor R. RP is equal to R1 multiplied by R2 divided by R1 plus R2. So 3.6 will be equal to R1, the total resistance on this path. That is 4 ohm, right? So we're going to have 4R divided by 4 plus R. 3.6 multiplied by 4 is 14.4 plus 3.6R is equal to 4R. So if I take 3.6R to the right hand side, I'm going to get 14.4 being equal to 0.4R. Now I just need to divide both sides by 0.4. I'm getting R being equal to 36 ohms. Right, 8.3.2. Let's move to the question that follows. 8.4. So in 8.4, they're saying that S1 is now open and S2 is closed. How will the power dissipated by the 4 ohm resistor change? Right, only increase, decrease, or remain the same? Explain the answer. So S1 is now open. Let's go ahead and show that S1 is open and S2 is now closed. So we have the current flowing in that direction. Initially, R external was 7.6. Now R external is just RS, which is 4 ohm. So clearly R external has decreased. If R external decreases, then the total current is gonna increase. What will happen to the 4 ohm resistor if the total current increases? It will dissipate more power because P is equals to I squared multiplied by R. R is constant, so if the current increases, the power dissipated should also increase. So the power dissipated by that resistor increases. 8.5, grade 12 learners conducted an investigation to determine the internal resistance of a battery. The circuit used is shown below. By varying the rheostat settings, the corresponding values of the circuit current and the potential difference V2 were recorded. V2 is the voltmeter reading across the rheostat. Let's go ahead and answer our question. 8.5, 8.5.1. From the graph, deduce the EMF of the battery. When the current is equals to 0, when there's no current flowing, the voltmeter is going to read the EMF. So if you look at our graph, when our current is 0, the potential difference is 4.5 volts. So we're going to have the EMF being equals to 4.5 volts. Another definition for the EMF, it is the reading on the voltmeter connected across the ends of the battery when there is no current flowing, just like in our case. Right, 8.5.2, calculate the internal resistance of the battery. Well, we're supposed to use the graph. How are we going to use the graph? You need to be comfortable with derivating an equation for the graph. Well, we know that EMF is equals to V external plus the current multiplied by the internal resistance. So V external is equals to the EMF minus IR. Well, as we can clearly see, our V external is our dependent variable, that is our Y, and our EMF is our intercept, that is C. Our current is what we are changing, that is X, and then minus the internal resistance is our slope. So we can say that the gradient is equals to minus R. Now we just need to calculate the gradient of this graph. Let's take this point as it is easy to read, and this point. Okay, so VF minus VI divided by IF minus II. Right, so what is VF? Let's use this point as our second point. So we have 1.5 volts minus this point, which is 3, divided by IF, that is 5, minus I initial, which is 2.5. This is equals to minus 0.6. So if we divide both sides by minus 1, we're going to get the internal resistance being equals to 0.6 ohms. And just like that, we have answered 8.5.2. The variable resistor R is set at a resistance of 3.5 ohms. So instead of having that R there, let's put 3.5 ohms. And then the first question, 7.1.1, let's calculate the total resistance of the circuit, including the battery. Right, so we're going to have RT being equals to RS plus RP. But we are required to include the resistance of the battery. So let's have plus the small r, which is our internal resistance, by the way. The resistance in series is just going to be the resistance of this variable resistor. It's the only resistor that is in series, right? R1 plus R2 and so on. This is sort of the formula we use. But then in this instance, we only have one resistor in series. So we're just going to have 3.5 ohms. And then now, let's go ahead and find the resistance in parallel. We're going to have 1 divided by RP being equals to 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3 and so on. So we're going to have 1 divided by RP being equals to 1 divided by R1. So the resistors in parallel, this 10 ohm resistor is in parallel with this 30 ohm resistor. Why am I saying so? I'm saying so because the current flows from the positive terminal to the negative terminal. So when the current is flowing at this point it divides. A proportion of the current comes to this path and another proportion of the current comes to this path. So that is why we're saying that those two resistors are in parallel with each other. So we're going to have 1 divided by 10 plus 1 divided by 30. So RP is equals to 1 divided by 10 plus 1 divided by 30 to the minus 1. If you put that in your calculator, you should get 7.5 ohms. So there we go. We have RP. The internal resistance is given to us right here is 0.6 ohm. So that is to say that RT, the total resistance, will be equals to the resistance in series, which is 3.5, plus the resistance in parallel, which is 7.5. And then lastly, the internal resistance, which is 0.6. You add all that and you'll get 11.6 ohms. And that is the total resistance of our circuit, including the battery. Let's move to 7.1.2. 7.1.2. Let's find the current measured by ammeter A2. Let me just remove these lines so that we can have a bit of clarity. We're looking for the current in this ammeter A2. We're looking for the current in this ammeter A2. So what are we looking for? We're looking for the current. It will be quite easy to find the current if we had the voltage and the resistance, right? But it seems like we have the resistance. There's a heater there with a resistance of 10 ohms. So our resistance is covered. We know that it is equals to 10 ohms. What we can actually do here, we have VT. We have VT. We have the total voltage, right? And then we have the total resistance. We can find the total current. And then by finding the total current, we can then find VP. So let's go ahead and say that VT is equals to IT multiplied by RT. The total voltage is equals to the total current multiplied by the total resistance. The total voltage, that is 24 volts. And then the total current, it's what we are interested in, right? And then the total resistance, we calculated it to be 11.6. So IT will just be, so now it's just a matter of saying 24 divided by 11.6, which is equals to 2.069 ampere. So right, there we go. We have IT. Now that we have IT is just taking us a step closer to our answer. We're not looking for IT. We're looking for the reading on A2, and A2 doesn't read IT. So we can say that VP is equals to IT multiplied by RP. If you use this formula, you're going to be able to find the voltage that the heater experiences, or the total voltage on that path, that is. So VP will be equals to 2.069 multiplied by RP. I think RP is supposed to be 7.5. RP is supposed to be 7.5. And if you put that in your calculator, you shall get 15.53 volts. So now we have VP. Now we have VP. Let's go back to our initial information. Now we have VP. We can say that this V here is equals to 15.53 volts. So now we can go ahead and find our current, because we have VP. We're going to say that the current on that path will be equals to VP divided by the resistance on that path. So VP, that is 15.53, and then the total resistance on that path, it is 10 ohm. So it's easy to see now that the current there on that path should be 1.55 amperes. And now we have answered 7.1.2. 7.2, the variable resistor is now adjusted to have an even higher resistance value. So the resistance of the variable resistor is increased. So we no longer have 3.5 here. We probably have 10 or something. Whatever number is greater than 3.5. The question is saying, how will this affect the power dissipated by the heater right? Only increase, decrease, or remain the same. So what is the equation for power again? Power is equals to I squared multiplied by R. So what is going to happen when the resistance increases for the entire circuit? When the resistance increases, the current is going to go down. The current is going to go down. If the current goes down and P is directly proportional to I squared, then the power should also go down. It should decrease. So the answer to 7.2 should be decreases, as we can clearly see from our equations. Have you ever calculated the EMF using simultaneous equations? That's what we're going to do for this question, right? Look at 8.3. We have to calculate the EMF, but we don't have the internal resistance, right? But before we do that, let's do 8.2. So 8.2.1, we're looking for the reading on the voltmeter. So our voltmeter is connected across this 3 ohm resistor, right? As you can clearly see. So what you have to realize here is that the current splits at this point. So we have two parallel paths. These two resistors, the 2 and the 5, are parallel to the 3 ohm resistor. And then what do we know about resistors in parallel? We know that the voltage is the same, but the current is different, right? So to find the reading on the voltmeter, we can actually use this current we are given in A1 and multiply it by the resistance of these two resistors. We can find the VP by doing that, right? We know that if we do that, it's going to be the same value that is in the voltmeter, because the 3 ohm resistor is in parallel with the 2 and the 5 ohm resistor, right? So what are we saying? We're saying that we can have VP is equals to I multiplied by R. So VP will be equals to 1.5 multiplied by 7, right? Pretty much straightforward, no complications whatsoever. And then if you put that in a calculator, you should get 10.5. So the answer here for 8.2.1, we have 10.5 volts. That will be the reading on the voltmeter. Right, let's move forward and do 8.2.2. What are we looking for? We're looking for the reading on ammeter A2. So right, if we go to our sketch, you're gonna realize that ammeter A2 is here, right? So basically what we're looking for is the total current, because ammeter A2 experiences total current. So we're looking for IT. What do we have up to so far? We have VP, which is equals to 10.5 volts. What we're looking for is IT, right? But then we have a formula that says that VP is equals to IT multiplied by RP. So since we have VP, we can find RP, and then by doing that, we're going to ultimately find IT. So let's go ahead and find the resistance in parallel. We can say that 1 divided by RP is equals to 1 divided by R1 plus 1 divided by R2. So RP is equals to 1 divided by the total resistance on this path, which is 3 ohms, right? Plus 1 divided by the total resistance on this path, which is 2 plus 5. So we're supposed to have 2 plus 5 here to the power minus 1. And then if you put that in your calculator, you're going to get 2.1 ohms, right? So now we have RP. We can then say that VP is equals to IT multiplied by RP. So VP is 10.5. And then IT is what we're looking for. But what is RP? RP is 2.1. It's easy to see now that IT will be equals to 10.5 divided by 2.1, which is equals to 5 amperes. Right, so the value of IT is 5 amperes. Right, let's move to the following question. we're looking for the power dissipated in the 3 ohm resistor. So to determine power, there's quite a few formulas we can use. We can say that P is equals to V squared divided by R is equals to V multiplied by R by I, or it is equals to I squared multiplied by R. So let's see if we can use the first formula. We have the voltage, it is 10.5 volts, and then we have the resistance, which is 3. So we can use this formula. We don't have to try use any other thing. So we're gonna have P being equals to, what is the voltage? 10.5. And then we square that divided by the resistance, which is 3 ohms. Right. So now it's just a matter of putting that in your calculator. And then when I do that, what I'm getting 36.75. So I have 36.75 watts. Right, that is 8.2.3. And the question we're really interested in is 8.3. So in 8.3, we're told that switch S1 is now open while switch S2 remains closed. The reading on the ammeter E2 is now 3.64 amperes. So when S1 is open, now we have an IT, which is equals to 3.64 ampere. We have a total current which is equals to 3.64. So let's go to our sketch and see what happens when switch S1 is open. So when switch S1 is open, the current is no longer passing this point, right? So basically, all the current is gonna flow like this. All the current is gonna pass through the 3 ohm resistor. Right, so now our total resistance is 3 ohm. So to calculate the EMF, we can say that EMF is equals to I multiplied by R plus the internal resistance. So our EMF will be equals to the current, which is 3.64, multiplied by the external resistance, which is 3 ohms, right, plus the internal resistance. So EMF is equals to, so we have 3.64 multiplied by 3, which will give us 10.92 plus 3.64 R. As you can see, we're looking for the EMF, but we don't have the internal resistance. So we're stuck. We have one equation and 2 variables. So we can call this equation 1 and go ahead and try find another equation so that we can solve simultaneously. So this is when IT is equals to 3.64 ampere. But what happens when IT is equals to 5 amperes? Like we had when both switch S1 and S2 are closed, right? So now we can use this information. We know that the corresponding current is 5 ampere, right? So we're going to say that EMF is equals to I multiplied by R plus internal resistance again. So the EMF is equals to the current, which is 5 amperes when both switches are closed, multiplied by the external resistance, which is RP, right? That was 2.1, and then plus internal resistance. So the EMF is equals to 10.5 plus 5R, equation 2. So we can equate these 2 equations and determine the internal resistance and ultimately the EMF. So equation 2 is equals to equation 1. So what are we saying? We're saying that 10.5 plus 5R should be equals to 10.92 plus 3.64R. Right, so let's take 10.5 to the right hand side and take 3.64R to the left hand side. So if we take 3.64R to the left hand side, we're gonna get 1.36R, and then when we take 10.5 to the right hand side, we're gonna get 0.42. So R is equals to 0.4Q divided by 1.36, and that is equals to 0.31, actually not 0.31 but 0.3088 ohms. Right, so we have the internal resistance. We can substitute it into either equation 1 or 2 to find our EMF. So if we substitute it in equation 2, we're going to get 10.5 plus 5 multiplied by 0.3088. Right, so we have 10.5 plus 5 multiplied by 0.3088. I'm getting 12.044. So 12.044 volts seems to be our EMF. Right, and now this trick equation 8.4 is actually out of 4 marks. So what is it saying? We have switch S2 is now opened while switch S1 is closed. So let's go ahead and make that adjustment. S2 is now opened. So S2 is no opened. The 3 ohm resistor is no longer taking part in our circuit. We can essentially just erase this. Yeah, we no longer have that when switch S2 is now open. How does the voltmeter reading change? Actually, let's not erase it because now we cannot see our voltmeter. So let's just erase S2 alone. Let's just erase S2 alone. Right. Yeah. There we go. How does the voltmeter reading change? Choose from increase, decrease, or remain the same. So the voltmeter is reading V external, right? So what will happen to V external when that switch is open? The first thing to realize that R external increases. That's what's going to happen when that switch is open. R external is going to increase. But if R external increases, and we know that I is equals to V divided by R, then current decreases. If current decreases, and let me show you something, EMF is equals to I multiplied by R plus I multiplied by the internal resistance. If the current decreases and then our internal resistance stays the same, then V internal is going to decrease, right? V internal decreases. But we need the EMF to stay the same. So to combat a decrease in the internal potential difference, V external increases. So the answer that we're looking for here in 8.4 is actually increases, right? The reading on the voltmeter will increase. 3 resistors are said to be ohmic conductors. What does that even mean? It simply means that they obey Ohm's law. If a conductor is said to be ohmic, then it obeys Ohm's law. That is the answer to 8.1. The following question is saying that when switch S is open, the voltmeter V1 reads 3.2 volts. So we have a voltmeter V1 right here, and when switch S1 is open, it reads 3.2 volts. What we are required to do is to calculate the current through the battery. So let's look at V1. We have a voltmeter reading on V1 of 3.2 volts. We also have the resistance of 4 ohms, of which V1 is connected across. So this is our resistance. We are simply looking for the current. The current through our 4 ohm resistor is the current through the battery. Because, let me show you, we have the positive terminal here, and here we have the negative terminal. The current is going to be flowing, and as you can see, the current is not going to divide at this junction because switch S is open. So the 4 ohm resistor is going to experience total current, just like the 8 ohm resistor will. So that's why we're saying that the current through that 4 ohm resistor is the same as the current through the battery. So we're going to have V1 being equals to I multiplied by R. V1 is 3.2 volts. I is what we're looking for, and R is 4 ohm. So we're going to have the current being equals to 3.2 divided by 4. If you put that in your calculator, you should get 0.8 ampere. So that is the current through the battery, the current through the 4 ohm resistor, the current through the 8 ohm resistor. The question that follows, we are looking for the EMF of the battery. So EMF is given by the current multiplied by the external resistance plus the current multiplied by the internal resistance. So the EMF will be equals to, our current is 0.8. What is our external resistance? We have 2 resistors in our external circuit of 4 ohms and 8 ohms respectively. They are in series with each other, so we don't have to do anything complicated there. We can just add those 2 resistances and there will be our R external. So 4 plus 8, let's just write it down as it is. 4 plus 8 is our external resistance, plus 0.8 multiplied by the internal resistance. The internal resistance is 0.5 ohms. So we have 0.5. If you put that in your calculator, you should get an EMF of 10 volts. Let's move to the question that follows. So 8.3, when switch S1 is closed, so let's just erase this for the sake of clarity. Yeah, when switch S1 is closed, voltmeter V2 reads 8.8 volts. Let's go ahead and look at voltmeter V2. Voltmeter V2 is connected across the ends of a battery when there is current flowing to the external circuit, and it reads 8.8 volts. That is our V external. So we have 8.8 volts as our V external. So the V internal will be 1.2 volts. Right, let's hear what the question says. Calculate the resistance of resistor R. We want the resistance of resistor R. Let's write down the information we have down so that we can see an approach we're supposed to take. We have VP, which is 8.8 volts. Yeah, why am I saying that VP is 8.8 volts? Because when you close this switch now, these 2 resistors are in parallel with this resistor, and that is the only place where there is a potential difference. So VP is 8.8 volts. Well, we have, almost RP because we're looking for the resistance of R. So we can let that be our unknown variable. Yeah, because if we find RP, then we have R. So VP is equals to IT multiplied by RP. Can we calculate IT? Yes, we can. We can calculate IT. IT is not 0.8 ampere anymore because now the switch is closed. The current is going to change. So we have to calculate IT again. What can we say? We can say that EMF is equals to V external plus IT multiplied by the internal resistance. The EMF of the battery doesn't change. So it doesn't matter that we've closed that switch. V external and V internal, they change such that the EMF will remain constant. So EMF is 10, V external is 8.8, and then plus IT multiplied by 0.5. 1.2, that is 10 minus 8.8, being equals to IT multiplied by 0.5. If we divide by IT on both sides, we should get a current of 2.4 ampere. Right, so now we have VP, RP, and IT. We know that VP is equals to IT multiplied by RP. So VP will be equals to IT multiplied by, so instead of writing RP, we can write R1 multiplied by R2 divided by R1 plus R2. VP, that is 8.8 IT, that is 2.4, multiplied by R1. R1, let's take the resistances on this path as R1, and we're going to take resistor R as R2. So R1, 8 plus 4, that is 12. So we have 12 multiplied by R, 12R, divided by 12 plus R. So we can divide both sides by 2.4. Let's go ahead and divide both sides by 2.4. 3.67 is equals to 12R divided by 12 plus R. Let's go ahead and cross multiply. We're going to get 12 multiplied by 3.67 plus 3.67R being equals to 12R. So 12 multiplied by 3.67 is equals to 12R minus 3.67R. So 12 multiplied by 3.67 will be equals to 12 minus 3.67, and then we take in R as a common factor. We can just divide by 12 minus 3.67 on both sides. 12 minus 3.67. We get R being equals to 5.29 ohms. Last question, the battery becomes heated when voltmeter V2 is replaced by a connecting wire. Explain this observation. Let's go ahead and do that so we can see what it is going to look like. So instead of having V2 there, we are replacing it with a connecting wire. So now we just have a wire that is connecting there. What will be the consequence of that? What's going to happen when we replace V2 with a wire? Well, all the current is going to go through the wire. We're not going to have any current go into the external resistors anymore. So we're going to experience what we call a short circuit. The current that is going to be flowing is very high, as we now only have the 0.5 ohm internal resistance. What is going to happen to all of that energy now? It cannot be created, it cannot be destroyed. It has to be converted from one form to another. In this case, it is going to be converted to heat, and that is why our battery is going to heat up.